Hi, this is the video for section 11.1 about the inference between two population proportions. The objectives in this section are 1. Conduct hypothesis tests regarding two proportions from independent samples, and 2. Construct confidence intervals to estimate the difference between two population proportions. So objective 1 is to conduct hypothesis tests regarding two proportions from independent samples. So when we have two proportions, that means we'll be using sample data from two independent samples to test a claim made about the difference between the two population proportions. So we'll call these P1 and P2. The requirements for this are 1. We have to have proportions from two independent simple random samples. And 2, for each of the two samples, the number of successes is at least 5 and the number of failures is at least 5. And this is a very simple way to determine if the criteria are met or not. Now our notation for two proportions is going to be a lot like the notation for one proportion, only now we have two populations and two samples. So we use subscripts to tell the difference between them. So for population 1, we have P sub 1, which is our population proportion, N sub 1, which is the size of the sample, X sub 1 is the number of successes in the sample, and P sub 1 hat is X sub 1 over N sub 1, which is the sample proportion. And for population 2, we have similar notation, only have subscripts of 2 instead of 1. So we have P sub 2, which is our population proportion, N sub 2 is our sample size, X sub 2 is the number of successes, and P sub 2 hat would be our sample proportion. Now another thing that we have to use in the formulas for two samples is a pooled sample proportion. So when we talk about the pooled sample proportion, this is just something that goes into our formulas, and this is basically taking our two samples and putting them together and getting an overall proportion using both of the samples and both of the sample sizes. So we call this just P hat without a subscript. And the formula for this is, again, on the top we just add the number of successes from each of the two samples. On the bottom we add the two sample sizes, and then we divide those two things. And our test statistic, when we're doing two proportions, this is a z sub naught. Again, when we're dealing with proportions, we're going to use the standard normal distribution. So we can tell that by the fact that we have a z here. So on the top we have just the difference between the two sample proportions, so P sub 1 hat minus P sub 2 hat. And on the bottom, underneath the square root, notice that we just have a P hat in here, which is our pooled sample proportion. So this is our pooled sample proportion. This is 1 minus that pooled sample proportion. And then here we have 1 over the sample size for the first sample plus 1 over the sample size for the second sample. Now remember, in the last chapter we talked about hypothesis testing and we went through those 5 steps. We're going to have the same 5 steps for these hypothesis tests. So step 1 is to determine our null and alternative hypotheses. Step 2 is to choose a level of significance alpha. Step 3 is to compute our test statistic. Step 4 has 2 parts, finding the p-value and then determining the initial conclusion. And step 5 is to state the final conclusion. Now step 1 for this is going to be a little bit different just because we have 2 parameters to deal with. So again, we're going to start out by writing down the claim or the statement being made in a complete sentence. And then we're going to translate that into an alternative hypothesis. So we're going to use P sub 1 and P sub 2 to represent our two population proportions. And then again, we're going to decide what inequalities should be used. It has to be either a less than, a greater than, or not equal to. And to figure this out, think about how the population proportions are compared in the claim. And then we're going to write all our alternative hypothesis in symbols. So first write the inequality with p sub 1 on the left side and p sub 2 on the right side. So you're either going to have p sub 1 is greater than p sub 2, p sub 1 is less than p sub 2, or p sub 1 is not equal to p sub 2. And the reason that we start with this is because it's easier just to think of how the two population proportions are comparing in the claim. Now once we have our alternative hypothesis written this way, for several things including StatCrunch, if you're going to use that, you need to have it written so that p sub 1 and p sub 2 are on the same side of the inequality with a 0 on the other side. So once we get it in this form, then we're just going to subtract the p sub 2 from both sides so that we have p sub 1 minus p sub 2 on the left side and 0 on the other side. That's not going to change our inequality. So again, once we have our alternative hypothesis, then we can write our null hypothesis just by replacing that inequality with an equal sign. So let's just do some examples of writing hypotheses. First example, an economist believes that the percentage of urban households with internet access is greater than the percentage of rural households with internet access. First we'll write the claim as a complete sentence. So the percentage, and remember percentage means proportion, of urban households with internet access is greater than the percentage or proportion of rural households with internet access. Now we want to translate this into an alternative hypothesis. So we do have to decide which our two populations are. The easiest way to do this is to make population 1 the one that's mentioned first in your claim, just because it's easier that way to translate it into an inequality. So let's say that our two populations are urban households, population 1, and rural households, population 2. So we're going to use p sub 1 and p sub 2 to represent our population proportions. And what inequality should we use? If we look at our claim, it's talking about the proportion of urban households with internet access being greater than the percentage of rural households with internet access. It actually uses the words greater than, so that would translate to a greater than symbol. Okay, so we would first write our alternative hypothesis as P1 is greater than P2. And then we're going to rewrite it by subtracting the P2 from each side so that we get P1 minus P2 is greater than 0. So there is our alternative hypothesis. Then our null hypothesis is just going to be this same thing with the inequality replaced with an equal sign. So it's going to look like this. Let's do another example. In clinical trials of a new vaccine, monkeys were divided into two groups. Subjects in group 1 received the new vaccine, while subjects in group 2 received a control vaccine. Drowsiness had been noted as a possible side effect of the vaccines, and researchers were interested in whether a different proportion of subjects in group 1 experienced drowsiness as a side effect than subjects in group 2. Again, we want to write our claim as a complete sentence. So, the proportion of subjects in group 1 that experienced drowsiness was different than the proportion of subjects in group 2 that experienced drowsiness. Now to translate this, again we're deciding what our two populations are. Since we already have it up here stated as group 1 and group 2, it would be easier to make those match. So let's say that our population 1 is those receiving the new vaccine, because that was group 1, and those receiving a control vaccine would be population 2, because that was group 2. And what inequality should we use? The claim just says that P1 is different than P2, so this translates to a not equal to. So we would start out by writing our alternative hypothesis as P1 is not equal to P2, and then we'd subtract the P2 from each side to get P1 minus P2 is not equal to 0. So there's our alternative hypothesis, And there's our null hypothesis that we get by replacing the inequality with an equal sign. Okay, now let's go through a whole example of doing a whole hypothesis test. So we've got some sample data here. This is a simple random sample of front seat occupants involved in car crashes. So the car either had an airbag available or didn't. And we have here in the table, we have the number of occupant fatalities out of the total number of occupants. So out of the 11,541 crashes where an airbag was available, there were 41 fatalities, and out of the 9,853 where no airbag was available, there were 52 occupant fatalities. So we're going to use the sample data and a 0.05 significance level to test the claim that the fatality rate of occupants is lower for those in cars equipped with airbags. Now this is one where if you saw this problem, you might have to think a little bit to realize that this was dealing with a proportion. When we're talking about the fatality rate, we're talking about the proportion of occupants out of the total that died. So we have our proportion of occupant fatalities is the same as our fatality rate. And if we want to compare the proportion of fatalities for those with airbags and for those with no airbag, we would look at this as two different populations. So our population 1 is those with an airbag available. Again, this was the first column in our table, and it was also the first one that was mentioned in our claim. And our population 2 is going to be those with no airbag available. So step 1 of our hypothesis test is to write our claim. So the fatality rate, and again we can make this specific so we remember it's a proportion. This is the same as the proportion of occupant fatalities is lower for those in cars equipped with airbags. Our parameter is the difference of the two population proportions, so it's P1 minus P2. And what inequality should we use? The claim says that P1 is lower than P2. So this translates to a less than. So we would first write our alternative hypothesis as P1 is less than P2, and then rewrite it as P1 minus P2 is less than 0. So there's our alternative hypothesis, and there's our null hypothesis with an equal in place of the less than. Now for step 2, in this case we were given the alpha, but we still want to think about what a type 1 error would be. This would be supporting the claim that the fatality rate is lower for those in cars with airbags when this is not actually true, meaning that the fatality rates are the same whether they're airbags or not. Now this error could lead to extra expense and extra regulations involving installing airbags in cars when it really doesn't save any lives. Now again, we were already given the significance level to use. This would be alpha equals 0.05. So for step 3, we're going to take our sample data from the table, and this gives us the following values for our first sample. Our sample size is 11,541. Our number of successes, which we're counting as fatalities, is 41. So our sample proportion for that first sample is 41 over 11,541. For the second sample, we have a sample size of 9,853, 52 successes, and here's our sample proportion. Now for this we have to do our pooled sample proportion, so we take our two numbers of successes add those on the top, and we take our two sample sizes and add those on the bottom. So there's our pooled sample proportion. And here's our test statistic calculation. So here we're subtracting our two sample proportions on the top, and on the bottom, remember we're using our pooled sample proportion in both of these places, and this is 1 over our first sample size plus 1 over our second sample size. And if you work all this out, it turns out to be approximately negative 1.91. Now for step 4, we need to think about what kind of test we have. So since our alternative hypothesis had a less than, this would be a left-tailed test. And remember, our test statistic formula used the symbol z, so that means we're using the standard normal distribution. So here's our picture. So we've got z equals 0 in the middle of our distribution, and here's where our test statistic was negative 1.91. And since we're doing a left-tailed test, we're shading to the left of our test statistic. Our p-value is the area of the shaded part here. And since this is a normal distribution, we would calculate our p-value by finding normal CDF. Looking at our picture, we're going from way over here, so we use a large negative number, to our test statistic, which is negative 1.91. Our mean is 0, and our standard deviation is 1. So if we calculate this, it turns out to be 0.0281. Our significance level was 0.05, so our inequality, p-value less than or equal to alpha, looks like this. We have 0.0281 is less than or equal to 0.05, which is a true statement. That means we have positive conclusions. So in terms of our null hypothesis, our positive conclusion would be that we do reject H0. And then for step 5, we're doing our final conclusion. So since we have a positive conclusion, we would say there is sufficient evidence to support our claim. So we would say there is sufficient evidence to support the claim that fatality rates are lower for those in cars equipped with airbags. Now we could also use StatCrunch to compute the values for steps 3 and 4. And anytime you're getting into 2 samples, the calculations get more and more intense, so it's a good idea to use some kind of software to help you. So to use StatCrunch, since we started out with summary data here, we would want to use the procedure that does a 2-sample proportion with summary. So in here we need to put in the number of successes and the number of observations, which is our sample size, for each of our 2 populations. So we have 41 and 11,541, and for sample 2 we had 52 successes out of our sample size of 9,853. And we're doing a hypothesis test, and notice here that when we rewrote our alternative hypothesis and our null hypothesis, we had a 0 on the right side, so we just use a 0 here. Our inequality was a less than. And here's the result we would get. And notice this gives us a whole bunch of different pieces that actually are part of our formula in our test statistic. So we've got our number of successes and our sample size for each of the 2 samples. The sample difference, if we look at our formula, the sample difference would be this part on the top, the first sample proportion minus the second sample proportion. So there's our sample difference. Our standard error is the part of this formula that's on the bottom. It's actually our standard deviation. So this whole thing, the square root on the bottom of this formula, would be our standard error. And then z-stat is telling us our test statistic. So that was negative 1.91. And this also calculates the p-value, which we found was 0.028. Objective 2 in this section is to construct confidence intervals to estimate the difference between two population proportions. And be careful with this because there is a difference between hypothesis tests and confidence intervals. Confidence intervals, for one thing, are always two-tailed, while hypothesis tests can be one-tailed, just as in the last hypothesis we just did. So they are not always the same. If you want to test a claim about two population proportions, you should use a hypothesis test. If you want to estimate the difference between two population proportions, in that case you should use a confidence interval. So to get a confidence interval estimate of the difference between two population proportions, that means that we're going to have our difference of our two sample proportions in the middle of our confidence interval. So we're going to start with that. We find our margin of error and we subtract that from our difference of our sample proportions to get our lower limit. And to get our upper limit, we take the difference in our two proportions and add the margin of error. And here's the formula for the margin of error. And again, this is more complicated because it's involving two proportions. But we still have z of alpha over 2, and we have p1 hat, which is our first sample proportion, p2 hat is our second sample proportion, and the n1 and the n2 are our two sample sizes. So let's take the sample data that we had from the last example and use that to construct a 90% confidence interval estimate of the difference between the two population proportions. And then we'll look at what the result suggests about the effectiveness of airbags in an accident. So our point estimate is the difference between our two sample proportions. So that is just subtracting our two sample proportions. So our point estimate is negative 0.001725. And we want to have a 90% confidence level. So that's one of our standard confidence levels, and since this is a Z, this is always going to be 1.645 for a 90% confidence level. And here's our formula for our margin of error. Here's our Z of alpha over 2. And here are our two sample proportions and sample sizes in the formula. And if we calculate this, our margin of error turns out to be 0.001547. Okay, so our confidence interval, we're taking our point estimate, which was the difference between our two sample proportions, plus or minus our margin of error. So when we do that, here are our two limits for our confidence interval. We have negative 0.003272 and negative 0.000218. The interpretation for this would be that we are 90% confident that the difference between the two population proportions is between negative 0.003272 and negative 0.000218. Now this is one place when we're talking about confidence interval estimates for two different samples or two different populations that it means something when we look at our two limits, whether 0 is included in the interval or not. So if we look at this interval, it does not include 0. Both of the numbers are negative. And because it doesn't contain 0, this implies that there is a significant difference between the two proportions. In other words, if 0 were included in the interval, then it would be absolutely possible that the two population proportions are the same. If 0 is not included in the interval, then we're saying that there's not as much of a possibility that the two proportions are the same, which means that they are significantly different. So this confidence interval suggests that the fatality rate is actually lower for occupants in cars with airbags than for occupants in cars without airbags. And the other nice thing about this confidence interval is that it also does give us an estimate of the amount of difference between the two fatality rates. Now, both of these numbers are very small because luckily we're talking about fatality rates in accidents, and hopefully that's going to be small. But we can still get a picture of what the actual difference between the fatality rates is. So how much difference it makes to have an airbag or not have an airbag.